The next tip is being able to create what we call a variable exitance source. So this is used to essentially define a non-uniform emission across a certain emitting surface. So one example we can think of is an LED typically will have a brighter spot in one area of the chip where the chip is located, as opposed to over the entire surface. However, if we just use a regular surface source, it creates a uniform distribution across the entire surface. So we might want to create what we call a variable exitance, where we can vary how the distribution is emitting across this emission surface. Some other examples of where this could be useful is for converting a RAY file source into a surface source. So RAY files are very commonly used, especially for LEDs, but they have certain issues and certain things that you can't necessarily do by using RAY files. So for one example, a RAY file will have a fixed number of rays. So for example, 10 million, 5 million. And that's a fixed number. You can't do more than that amount of rays. But for certain applications, you may need a larger number of rays to reach the precision that you need, as we looked at before. So this could be an example of where you want to convert that RAY file into a surface source, which has no limitation on numbers of rays. Another case is if you want to use an inverse simulation. RAY files are not compatible with inverse simulations. And finally, just as a general rule, surface sources tend to be faster to simulate as opposed to RAY file sources. The other time this could be used is to create something that's called a 2D light map. So essentially we pre-compute several sources in order to reduce the overall simulation time when we're running all of these sources through our light guide or through our whatever particular application we're using. So this method essentially involves defining the emission characteristics with a pre-simulation using a radiance sensor and an intensity sensor, and then using those outputs as an input into this variable exitance source. So the general process to create this variable exitance source is listed here. So essentially we create an irradiance sensor a small distance in front of, let's say, the RAY file source that we're trying to convert. So in this case, I've put it 0.1 millimeters in front of the source. The irradiance sensor can either be photometric, or if you're trying to keep the color of the emission, you can use a spectral sensor. We then put an intensity sensor at the same location, and this is going to capture the distribution of the light, so how the light goes in different angles coming off of this surface. And again, we can do photometric or spectral if you're trying to capture the color as well as the intensity. The higher sampling you use on each one of these sensors, the more accurate the conversion will be, but you'll of course require more rays in order to run that initial simulation. You then run a direct simulation using the RAY file source, the two sensors, and any LED geometry. And this will create two XMP results, which we then put into a new surface source using, in the exitance section, we changed the radio dial from constant to variable. And in the intensity section, we changed the type to a library. So we then put the irradiance sensor result into the exitance section and the intensity sensor result into the intensity section. And what this essentially does is we define the emission characteristics in the near field region using the irradiance sensor, and in the far field region using the intensity sensor. And this will capture all of the characteristics of that initial source distribution. The flux can be set manually if you know the output flux, or you can take it from the intensity sensor result using the little checkbox. And the spectrum can either be taken from one of the two results. So if you ran either the irradiance or the intensity as a spectral sensor, you can pull the color in from those results, or you can apply your own spectrum on top of this to change the color to whatever you need it to be. You can then do a preview to check that the axes are set correctly and the source is being emitted in the correct direction. So this is a typical example for converting a ray file into a surface source, but we can also use it to do what we call 2D light mapping. So essentially taking a series of sources, so in this case we have 6 LEDs in front of 6 collimators, and we take that entire assembly and build a light map which defines the output of all of these sources together as one distribution. So you can see that here. We use the exact same process that was just shown, putting an irradiance sensor directly above the emission surface, an intensity sensor which captures the distribution. And from that, you can see the result that's created on the right, which has the 6 circles for each one of these collimation features, as well as the rays that are representing the intensity distribution. And what this allows you to do is you calculate all of this as a pre-simulation so that it doesn't need to be put into the actual longer-term simulation. You can just go based on this pre-calculated distribution, which saves time, especially if you're running many simulations on the same design.